So let's continue our discussion. We'll be cleaning up and finishing up the chapter on acid-base chemistry and talking a little bit about how to rank all of the different effects that we discussed that impact acidity and basicity. And last session, we discussed inductive withdrawing groups and inductive donor groups. And we're now going to drill down on this idea of inductive effects and look and see how inductive effects impact the acidity of a very important proton, both for later chapters and for the second class in this series, which is the alpha proton to a carbonyl functionality. So for example, we can see inductive effects quite clearly if we compare a ketone to what do we call this second functional group? What do we call this functional group here? Not just a normal halide. It's a derivative of a ketone-like functionality that we call, what was that? Not quite an aldehyde, but it's called an acyl chloride, which is a specific subclass of the acyl halide functional group. Now, as we notice, is chlorine more or less inductive withdrawing compared to carbon? More. Yeah. So we have an inductive effect that's pulling electron density away from our carbonyl carbon, which in turn pulls electron density away from the carbon attached to our alpha proton. So if we draw out our conjugate base, so suppose we do manage to generate an alpha anion, will this anion be stabilized by this inductive withdrawing effect? Will this anion experience a stabilizing effect when it's adjacent to an inductive withdrawing group? Or when the inductive effect overall is more pronounced with chlorine compared to carbon? Is that anion more stable? What was that? So in general, when you're stabilizing an anion, do you want them adjacent to withdrawing groups or donating groups? Withdrawing groups, right? So if we have an inductive withdrawing group, is the resulting anion more or less stable? More stable. So then what happens to the acidity? If our conjugate base is more stable, what happens to our acid strength? Increases. So that's why the pKa is smaller. It's a more acidic proton because we generate a more stable anion. This is the textbook method of assessing acid strength that we looked at last time. We write out the structure of our conjugate base, we assess its stability, and that in turn allows us to conclude whether it's a stronger or weaker acid. Does that make sense? Okay. So, another important idea is that when we have less electronegative atoms attached, we can end up where these less electronegative atoms will donate electron density to adjacent atoms that results in destabling our anion and a less acidic proton. So for example, when we look at a ketone enolate or an anion of the following ketone, and we compare that to the formaldehyde anion, as we discussed during our review, and as we can see from the pKa values, what do you expect to exert a stronger donating effect? This alkyl chain or a hydrogen atom? Which species is donating more electron density into our system? The alkyl chain. So let's draw that using a different color. So this alkyl chain is donating electron density into our system. Now, as a result of this inductive donation, what happens to our alpha proton pKa? What happens to this anion stability? Is it more or less stable if we're shoving electron density into and adjacent to our anion? Less stable. Negative charges repel. So this inductive donation is destabilized. And as a result, would we expect our alpha proton to become more or less acidic as a result of this destabilizing interaction? Less, exactly. So that's why aldehydes are, in general, easier to deprotonate at the alpha position, because hydrogen is such a weak donor. It doesn't have a lot of electron density to give. Okay, now if we compare a secondary to a tertiary alcohol, you also observe a similar trend in pK. The more substituted your overall acidic region, or your overall regions adjacent to your acidic atom, the more substituted it is, the more electron rich it is, and as a result, the less stable your anion and the higher the pK. So you can also rationalize an effect that we attributed to sterics due to this inductive effect as well. So sometimes you see these subtle differences in pK, not only as a result of just one effect. So this isn't just solely a steric effect. There's also a little bit of contribution in terms of these inductive donating effects. Does that make sense to everyone? Yes. How many carbons do we have attached? Yes. So how many do we have? 3. Yeah, exactly. And we have a secondary alcohol because we have 2 substituents. Yeah. Okay, let's keep going. Let's talk about a very interesting system that requires us to consider the combination of inductive and resonance effects together. So in this case, we're looking at an alpha proton series where we're comparing the alpha proton of a range of different carbonyl-like substituents. So these are some common pKa values that I want you to be familiar with and able to rationalize. So if we think about this table, as we go from the left to the right, what is a general feature of these functionalities on the left? Do we see a lot of inductive and resonance donors, or inductive or resonance withdrawals? So on the left, so for example, let's look and let's try to draw some resonance structures. Is this amine functionality in our amide a resonance donor? Is it dumping in electron density to our central carbon? Yes. Is this ether-like functionality in our ester? Is that also a resonance donor? Yes. So we notice these 2 species are resonance donors. And what did we say about resonance donors? If we're pushing electron density adjacent to our anion, is our anion going to be more or less stable? If we push electron density adjacent to our anion and we put our negative charges next to each other, is that stabilizing or destabilizing? Destabilizing. Yes, you had a question?
So what if we were to look at the hydrogens that are on the right side of the nitrogen and the oxygen? Would it then be considered electron withdrawal?
Those protons in general are substantially less acidic because the protons alpha to an amine are very similar. They're a little bit more acidic than an alkyl group, but not by much. So they're generally not deprotonated. In general, when you're analyzing a system, you always focus on the most acidic sets of protons. And that's why I drew this as a tertiary amine. So that way we didn't have to consider the hydrogen attached to the amide nitrogen. Does that make sense? Perfect. Now, if we compare these resonance donors that have relatively high pKa's and are relatively weak acids, what has changed when we move from an ester to a ketone? Are we dealing with resonance donation anymore? No. What do we call this type of donation? When it's due to electron withdrawing or electron donating capabilities. Inductive, yeah. So now we have an inductive donor. Okay, and looking at our acyl chloride, is it an inductive donor or withdrawer? Withdrawer, yeah. So we have an inductive effect. So we have an inductive withdrawer. Now, what's so special about the nitro group? Why is nitromethane super acidic? Is it just a inductive withdrawal? No. What is it also able to do? It's a resonance withdrawer. And to help everyone see that, let's draw a potential picture. Let's draw a picture of this nitro group. And let's look at the anion generated. So now that we have this anion from our nitro group, oops. Can we delocalize our anion? Can we delocalize our anion via resonance into this nitro group? Yes. So now it's not just inductive withdrawing, it's also resonance withdrawing. You can take your electron density and it's withdrawn and distributed into that functional group. That's why nitro groups lead to especially high alpha proton pK, because they're not only inductive withdrawing, it's also a resonance effect. So it's additive. Does that make sense? And that explains why if you compare an acyl chloride to an acyl chloride, for example, to a nitromethane alpha proton, the difference in pK is almost 1 million in terms of relative acidity. So let's make this really explicit. So when we think about oxygen, we generally think of oxygen as a more electronegative atom. That is 100% correct. But in addition to having an inductive withdrawing effect, does it also have a lone pair that can participate in resonance? Can it also donate a lone pair? Yes. So it's a resonance donor. Now, as a result of this resonance donation, as a result of this donor characteristic, so as a result of this resonance donor characteristic, we're shoving our electron density into our carbonyl carbon. Now, as a result of this donation effect, this carbon in our ester is more electron rich. Okay. Now, what is the consequence of that? What is the consequence of that? If we compare our anions, if we compare our two possible anions that we can generate, we compare our ketone anion versus our ester anion. My question to all of you is, which of these carbonyl groups will exert a stronger inductive effect? This is another way of thinking about this problem. Which of these carbonyl groups is more electron deficient? Which of these two carbonyls? The carbonyl in the ketone or the carbonyl in the ester? Considering our discussion of the resonance forms, which one of these carbonyls is more electron deficient? What was that? Ketone. Exactly right. So this ketone functionality is more electron deficient. So then, if we try drawing out some resonance structures for these molecules, the one thing that you immediately notice, the one thing that you can immediately notice when you start trying to draw resonance structures is that your resonance donor is pushing electron density or attempting to push electron density. Let me use a different color for that. Or attempting to push electron density into our carbonyl. Notice we have two donor-like species. Your anion, which we're trying to delocalize and stabilize via resonance, and our resonance donor group that is also pushing electron density into our carbonyl. Is this interaction where we have our resonance donor dumping electron density adjacent to our anion, is that stabilizing or destabilizing? Destabilizing. Yep. So this is a destabilizing donation. And that explains why the ester anion is substantially less stable and why esters overall are less acidic. Yes?
So what is the blue arrow represent?
The blue arrow represents sort of the resonance donation effect. It's not part of the formal resonance structure, but it's just helping to convey that this lone pair, most of its density is being delocalized into our carbonyl. And as a result, we're not able to as efficiently delocalize and stabilize our anion lone pair. We don't like to push large amounts of electron density into a small number of atoms. Does that make sense to everyone? Okay. So this is really important to consider and really important to keep in mind. So I know this seems obvious, but it's a very important thing always to be aware of. Resonance effects require the anion to be conjugated to the resonance acceptor. So, for example, let's try to take a look and explain which of the following protons is more acidic. So which of the following protons, the proton in purple or the proton in green, which one of these protons is more acidic? And in order to answer this question, when we're thinking about comparing acid strength, what's the first thing that we draw? Yep, and what do we call that anion? Conjugate base, exactly right. So let's draw each of our conjugate bases. So let's draw each of our conjugate bases here. Okay, so here's our first conjugate base, and let's look at our second conjugate base. In the arrow ring? No, since they're all delocalized. Okay, so now that we have both of our conjugate bases, let's try using arrow pushing notation to get the lone pair on our anion into our nitro group. If we can do that, then the nitro group can efficiently act as a resonance withdrawal. That's our goal. You should be able to push your lone pair into the resonance withdrawal. So then, I'm going to switch pen colors for that, and we're going to do this in arrow pushing notation in red. So I'm going to push my lone pair down. That kicks the double bond one space over, and we can delocalize our double bond electrons to form a double bond with our nitro group. This then breaks the nitrogen-oxygen double bond, and in turn generates an additional lone pair on our nitro group oxygen. Okay? So let's now draw out this resonance structure, and let's talk about the implications of this resonance structure. So we are able to draw the following arrow pushing notation, which in turn leads to the following resonance structure. Let me just make sure I have my bond positions correct. So in turn, we've been able to generate the following resonance structure in red. Have we successfully delocalized the lone pair on our oxygen, on our conjugate base, into the nitro group? Yes. Let's try unsuccessfully to use arrow pushing notation for the structure on the right. So I'm going to try to kick my lone pair down. My double bond gets kicked across. My double bond gets kicked across. And no matter how hard I try, there's no way for me to delocalize that lone pair into the nitro group. And you're welcome to try as much as you want with arrow pushing notation, but there's no way in the following arrangement of atoms to delocalize our lone pair into the nitro group. So the key feature of this arrow pushing diagram is that our lone pair cannot be delocalized into the nitro group. Now, because of that, which of these two lone pairs, the lone pair in the structure on the left or the lone pair in the structure on the right, is more stabilized, more delocalized via resonance? What? Exactly. So then, which anion is lower in energy? The one on the left, which is heavily delocalized, or the one on the right, which is less delocalized? One on the left, right? The more delocalized your anion, the more stable it is, the lower in energy it is, and because we have a lower energy conjugate base, which species is more acidic? The structure on the left or the right? Left. Okay. So this anion, so we have a more stable anion. And as a consequence of that, if we go up to our comparison of our two structures, we would label the structure on the left as more acidic. Perfect. So we've used our capacity to draw resonance structures to write conclusions about which species is more acidic. And in this analysis, you're always writing out the conjugate base and checking the potential resonance delocalization of your anion. Does that make sense? Okay. Let's keep going with a few more examples. So let's talk about one last factor that affects acid strength, and it's relatively pronounced. So let's switch pen colors for that. So one of the major factors that impacts acid strength is charge. So remember when we discussed the impact of charge last class session? Charge can make an atom behave as if it's more electronegative than usual. It affects its relative behavior in terms of its relative electronegativity. So when you have protonated a species that is positively charged, do we notice that it's more or less acidic? So if we compare hydronium, H3O plus, to water, what's more acidic, the positively charged or the neutral species? Positively charged species. So the larger the positive charge, the more acidic the protons attached to that atom are. This is a general rule. The more positive charge you build up, the more your atom behaves as if it's electron deficient, and the more readily it's able to stabilize a potential negative charge or lone pair that you make when it's deprotonated. Okay, let's keep going and let's look at another example. So we have all these rules. How do we arrange these rules into a more procedural method of looking at compounds and ranking them in order of acidity? Okay, so I've developed in order of importance, but I always have to note these are not 100% definitive. This order is in general true, but there are exceptions, and we'll encounter a lot of these exceptions in this class. So in general, one of the greatest effects on acidity is charge. So the larger your positive charge, the more acidic your compound will be. So charge is usually the most pronounced effect on proton acidity. Next are atom effects. So your atom electronegativity and atomic size, with size playing a much greater role than electronegativity, right? We've seen in our example, in our little overview of electronegativity, the more electronegative your atom becomes, what happens to acidity? Does it increase or decrease? Increase, right? As we see if we go from methane to hydrofluoric acid is more acidic because fluorine is more electronegative, exactly. Likewise, if we look at atomic size has a much larger effect than just electronegativity. And as we go from hydrofluoric to chloric to bromic to hydroiodic, in general, as our atom size increases, what happens to our acidity? Increases, yep. Now, the next effect, and resonance can beat out atom effects in certain cases. So resonance effects Quite simply, if the conjugate base is stabilized via resonance, then the acid is more acidic. So our classic example is comparing, for example, an alcohol to a carboxylic acid. And what did we discuss was the key reason why carboxylic acids are more acidic. If we compare our conjugate bases, is the conjugate base of a carboxylic acid more delocalized? Yes. And that resonance delocalization stabilizes our anion. Now, when you think about resonance, you also want to consider where, or more correctly, what atoms. Let's consider what atoms are receiving the negative charge. So the reason why acetic acid is particularly strong, the reason why carboxylic acids are particularly strong, where is our negative charge being delocalized? Is it being delocalized to a carbon or an oxygen atom? Oxygen. So is it being delocalized over multiple electronegative atoms? Yes, and that's especially stabilizing. So it's not just the fact that charge is delocalized, but the fact that it's delocalized over very electronegative atoms. Okay, let's continue on, and this is just our nice little review of each of these components. So the next major effect are inductive effects. So in the case of our inductive effects, let me draw this structure out. So in general, the more inductive withdrawing groups that we have, what happens to our acidity? If we have more inductive withdrawing groups, more electronegative groups, what happens to our acidity? Increases, right? Quite simply, the more electron withdrawing groups you have, the more you're able to stabilize your anion, stabilize your ball of negative charge that you're generating. And it's almost linear. The more chlorines you tack onto your molecule, the lower your pKa becomes. Now, inductive effects and this next effect, which are orbital effects, are very close in magnitude. Now, what are orbital effects? Quite simply, anions are more stable if lone pair electrons are in a lower energy orbital. So for example, what's the lowest energy orbital and what's the most stable anion? On an sp, sp2, or sp3? Sp, right? So the more s character you have, the more stable your anion is. So an sp anion is more stable than an sp2 anion, and in turn is more stable than an sp3 anion. And we see that reflected in the pKa. An alkyne is actually not too bad to deprotonate. A vinyl proton is relatively hard to deprotonate, and good luck deprotonating a normal alkyl group under normal conditions. It has a pKa of around 50. It's not acidic in any sense of the word. Okay, the last major effect that really is a bit of an afterthought is solvation. So the less steric congestion around the acidic proton, the more acidic the proton. So essentially what I'm trying to say is the more substituted your acidic atom is, or the carbons adjacent to your acidic atom, the least acidic that proton becomes. So as we go from primary to secondary to tertiary, as we start crowding, adding steric hindrance, adding more things, taking up space around our acidic proton, what happens to the pKa? Does it increase or decrease? Are we getting more or less acidic? Less acidic. That's why our pKa values are becoming larger. Does that make sense? This effect is relatively minor, but it does pop up. It's why when you typically do acid-base reactions, if you need a stronger base, you're going to use tert butoxide instead of ethoxide, for example. Okay, so what are we going to do from here? So what we're going to tackle next are a set of interesting examples and exceptions. So we're going to go through some of the common exceptions that we'll encounter. And one of the main exceptions that I want us to talk about and go over together is an observation concerning the alkyne proton, which has a pKa of approximately 25, and an amine proton. What is the pKa of an amine proton? Looking at our pKa table. Let's consult our pKa table and let's try to write down what is the pKa of an amine roughly. That's an alcohol, but very close. Very close. 35. It's okay. It's okay. The more we practice with this, the more familiar we'll become. Now, this may seem like an innocuous piece of data. Would someone like to tell me if we use our typical rules involving in our typical ranking hierarchy? So in our hierarchy, we have our atom effects, right? We have atom effects as number 2. And then all the way at number 4, we have hybridization, right? So in an amine, we have an sp3. In an alkyne, we have an sp atom attached to our acidic proton. So if we use the hierarchy that I just told you, and this is why this is an exception that you'll need to be familiar with, we would expect which of these two species to be more acidic using this hierarchy. Just straight away as is. We would expect the amine to be more acidic, right? However, in this case, because there's a large difference in hybridization and our atom effects, there's not such a large difference in atom electronegativity, the hybridization effects went out. This is one example of an exception. The rules that I provided you will work about 90% of the time. The other 10%, you'll notice these odd edge cases. And this is why you need to be familiar with some of the common pKas so you can tease out some of these edge cases and then attempt to explain it. So to help explain the observed pKa values, we'll draw out each of our anions. Let's draw out each of the anions generated. So in this case, we have an anion on an sp hybridized atom compared to our anion on the amine, which is on an sp3 atom. So our rationale for why the alkyne proton is more acidic is quite simply the sp hybridized atom is more, sp hybridized anion is more stable. And that in turn leads to a more acidic proton. So this is a case where hybridization won out over atom effects. Does that make sense? Okay. Let's now look at a few other exceptions. And what we're going to do is there are a few other practice examples that we have in the supplemental notes. What we're going to do is we'll save those for you to work on at home, and that we're going to move on now to chapter 3, which has additional supplemental topics. So now that we've covered a few examples on acid-base chemistry, what we're now going to move into are the properties of alkanes, which are your most generic carbon-based functional groups. So we're going to look in this chapter procedures for naming alkanes, thinking about the energy of alkanes, and then assessing the three-dimensional arrangement of atoms in alkanes. Okay? So starting off, let's get to define a little bit about what is an alkane. What is an alkane? So an alkane is a saturated hydrocarbon that contains only carbon and hydrogen atoms and contains only single bonds. So they're relatively simple systems from a structural perspective. Alkane names end with ane. And a nice little rule to remember, you know that you're dealing with an alkane if it has the general formula of CnH2n plus 2, where N is just the number of carbons we have. Okay, so let's look at some common alkanes and let's try to get a sense of their properties and reactivity. So we have methane, ethane, propane, and butane. Let's count our carbons. So for methane, we have CH4. So this is N is equal to 1. For ethane, how many carbons do we have? 2. And how many hydrogens do we have? 6. For propane, using this formula, before you count, if we have 3 carbons, how many hydrogens would you expect? 8. Yep. And as we see, propane has the formula C3H8. You can do this counting method for all of your alkanes. They all have the formula CnH2n plus 2. Now, an interesting feature, if you have more than 3 carbons, you can end up with more than just one structure. We can start to generate constitutional isomers. Same number of atoms, different connectivity. So, for example, C4, if we have 4 carbons, you can have butane and isobutane. When you have 5 carbons, you can have pentane, 2-methylbutane, 2,2-dimethylpropane, just to name a few. So you have access to a broader number of constitutional isomers, the more carbons you have to work with. Makes sense. Now, alkanes with carbons connected to no more than 2 other carbons. So if we only have primary and secondary carbons, we call these straight chain or normal alkanes. So they're given the prefix N. So this would be N-butane. And we'll talk about where we got the butane from in a moment. Now, alkanes with 1 or more carbon connected to 3 or 4 carbons are known as branched chain alkanes. And depending on the exact branching of these constitutional isomers, they have different prefixes. Now, additionally, the naming of these branched alkanes will depend a lot on where this branched substituent is located, where the branching occurs, and how it's connected to your broader chain. And we'll talk about rules for branched alkanes in a moment. What we're now going to do is we're going to take a deep dive into the names of our straight chain alkanes, and then we're going to talk about the systematic rules for naming these organic molecules, so that way we can more efficiently communicate structure without having to just draw the structure every single time. So these are the names of your straight chain alkanes. So you have methane, ethane, and so forth. Let's now talk about the procedure for systematically naming these alkanes. And this is something you'll have to be familiar with. This is organic nomenclature. So an alkyl group, otherwise known as an R group, it replaces a carbon-hydrogen bond with a carbon-carbon bond to the main chain. Okay, so what do I mean by that? If you're describing an alkyl group, which is a side chain, an alkyl chain attached to a broader carbon chain, the way that we represent that it's an alkyl group is we replace the ane ending, which describes a normal alkyl chain, with the YL ending. So this YL is telling us that we've tacked on this group to a longer chain of carbons. So for example, CH3 substituent is a methyl from methane. So looking at methane, if you take off one of its carbon-hydrogen bonds and you replace it with a bond to our carbon chain, instead of having methane, you have a methyl group. Does that make sense? It's saying I have this methane substituent attached to my broader chain. Now, we can get very creative here, and from these alkyl groups, we can go about creating more complicated names for alcohols, amines, etc., that have this alkyl group. So for example, if we, instead of having a bond to a carbon chain, we bond it to an alcohol substituent, we go from methane to methyl alcohol. Because it's an alcohol with what group? A methyl group. Likewise, if we replace and instead attach our methyl group to an amine, it's named methylamine because we have an amine with what group on it? Methyl group, exactly. So here are some common straight chain alkyl groups. You're going to need to memorize the prefixes for each alkyl chain length. So methyl or methane is a 1-carbon substituent. So methane turns into methyl, often abbreviated as ME. Ethane is 2, and it gets abbreviated to ethyl, ET. Propane is 3, butane is 4, and pentane is 5. So you're going to need to memorize the prefixes that indicate the number of carbons in your chain. And once you know the prefixes, you can name your alkane and your alkyl groups. Does that make sense what you're expected to memorize? Just the common prefixes that indicate the number of carbons. Okay. Let's now talk a little bit about how we classify alkyl groups. How do we label and classify our alkyl groups? They're classified by the connection site of the parent chain. So quite simply, depending on where and how many carbon substituents are attached to a given carbon, we designate it as primary, secondary, tertiary, or quaternary. So for example, a primary carbon, it's a carbon that's attached to 1 carbon. So we give it this symbol of 1 primary. A secondary carbon, would someone like to take a guess, is attached to how many carbons? 2. Okay, and we give it a 2 primary. A tertiary carbon has how many attached? 3. Yep. And a quaternary carbon has how many carbons attached? 4. Okay. Is there a pentary carbon? Can you have more than 4 things attached to a carbon? No. We don't have any super hypervalent carbons or anything like that. Now, we can label alcohols, hydrogens, and halides as primary, secondary, or tertiary based on the carbon the substituent is attached to. So a primary, secondary, or tertiary halide is attached to a primary, secondary, or tertiary carbon, respectively. So let's label each of these carbons as primary, secondary, and tertiary, and let's in turn assign each of our hydrogens as primary, secondary, or tertiary. So, looking at the carbon farthest on the left, how many carbons are attached to the carbon that I've indicated with an arrow? How many carbons? How many carbons? Just 1, right? So then this would be primary, yep. And as a consequence, we label our hydrogens as primary, okay? How many carbons are attached to this carbon with this arrow? 2. So then it would be a secondary, exactly. Finally, looking at the following carbon, how many carbons are attached to our highly substituted carbon? 3. Okay, so this would be tertiary. Okay, let's try a few more examples. Let's classify the following alcohols, hydrogens, or halides as primary, secondary, or tertiary. I'll start us off with the following species. This is known as a T-butyl chain. This is like tert-butyl bromide. And this carbon here has 1, 2, 3 substituents attached, so it's tertiary. So this bromide would be a tertiary bromide. What I want you to do now is to break into groups and work on the next 3 on your own, and then we'll come together to discuss in about a minute and a half. Everything going okay?
On the next slide.
Oh, yes, your question that identifying it's isopropyl. So that's how it's for now, it's just identifying the alcohol.
Yeah, I can get and should be, yeah, that's what who's gonna get. No, he's gonna give us 2 hours.
It's fine, so it's just-
Yeah.
Yeah, exactly. Which carbon?
Secondary. So that, the second one is secondary, right?
Yep, exactly.
Secondary
Let's refer specifically to so in this case, I classify this as a tertiary halide.
and the next one is primary, secondary, tertiary.
Exactly. This is hydrogen, primary, secondary, tertiary.
carbon.
Exactly. Perfect. So let's talk a little bit about this. So would someone like to volunteer for this alcohol, which is known as isopropanol or isopropyl alcohol? Is the carbon that the alcohol is attached to primary, secondary, or tertiary? Secondary. So we classify this alcohol as secondary. Looking at the carbon that this hydrogen is attached to, is that carbon primary, secondary, or tertiary? Primary. Okay, finally, looking at the carbon that our chlorine is attached to, is that carbon primary, secondary, or tertiary? Primary. Perfect, perfect. Now you may say, why are we going through the trouble of classifying something as primary, secondary, or tertiary? Substituents that are primary versus secondary versus tertiary, as we observed even in the acid-base chapter, have slightly different reactivities and slightly different properties. So being able to identify your primary, secondary, and tertiary substituents can help you differentiate their reactivity and differentiate some of their potential physical properties. Okay. Now, let's talk a little bit about branched alkyl groups. So we call the normal chain an N-alkyl chain. So for the first major type of branching that we see are isoalkyl groups. In an isoalkyl group, our parent chain or carbon is attached to the secondary carbon. Okay? So for example, we have an N-propyl chain. It's propyl because it has how many carbons? 3. So prop is 3. So this is a propyl chain. R is representing our main chain. It's just showing you where are we putting this alkyl chain. Now, if we move our main chain from carbon 1 to carbon 2, if our main carbon chain is now attached to carbon 2, instead of an N-propyl, instead of just a straight chain arrangement, we call this an isopropyl or ipropyl chain. Does that make sense? Okay, so this is one constitutional isomer. The old, yes, yeah. Or in this case, quite simply, more straightforwardly, the second carbon in the propyl chain. Now, another potential constitutional isomer you can generate is best seen when we start looking at the butyl chain constitutional isomers. So a tert alkyl group has 3 carbons attached to the carbon attached to the parent chain. So in other words, I like to think of it that the parent chain or carbon is attached to it, the tertiary carbon. Okay, so let's look at all the potential butane chain isomers. So we have our N-butyl chain, which is our normal straight chain. It's butyl because we have 1, 2, 3, 4 carbons. 4 carbons, butane, butyl chain. Now, for isobutyl chains, we have rearranged our overall connectivity of atoms so that we now have a carbon attached to our secondary carbon. We have a carbon attached to the second carbon in the chain. This is called isobutyl. Does it look pretty similar to isopropyl? Okay. Now, the next major variant involves a constitutional isomer with a tertiary carbon and our main chain attached to that tertiary carbon. You'll want to be familiar with each of these common alkyl chains as they pop up a lot in organic chemistry. Any questions so far? For those curious why isobutyl and isopropyl look a little bit different, the key distinction between isobutyl and isopropyl, in both cases, we have a carbon attached to the secondary carbon, right? We have a carbon chain or a carbon attached to the second carbon in this chain. But if we, for example, had our alkyl chain attached at carbon 2, it would actually get an entirely different name. So there's a way to account for differences in position of our alkyl chain, as well as differences in the connectivity of atoms in our alkyl chain. The iso prefix refers specifically to how are the atoms connected in our chain. Does that make sense? Okay. So, to immediately address this point, another common prefix and another common constitutional isomer are known as Cyclo Alkyl Groups. In this case, in a Cyclo Alkyl group, the parent chain is attached at our secondary carbon. So the main difference between N-butyl and Cyclo-butyl, Cyc as in quote unquote secondary, if we count our carbons, 1, 2, 3, 4, 1, 2, 3, 4, where is our R group in the Cyc-butyl chain? Second carbon, exactly. It looks exactly like a normal straight chain alkane, except the Cyc is telling us our main chain is on the second carbon instead of the first. Does that make sense? Okay.
So what is the difference between and loss or something?
Yeah.
What's the difference between that one and the iso?
So in the iso case, so for example, if we're comparing like isopropyl and isobutyl, the iso prefix tells us that we have a carbon or a chain attached to a secondary carbon, attached to the second carbon in the chain. The Cyc prefix tells us that our main chain specifically is attached to the second carbon. So the Cyc prefix tells us we have a normal N-butyl chain, but the main chain is on the second carbon. So the Cyc prefix tells us a lot about where the main chain is located. Does that make sense? Perfect. So let's keep going and let's now look at, well, how do we go about naming alkanes? So naming alkanes can be brought into a 4-component set. So first things first, we have our locant. So this is a number that tells us where are the substituents or functional groups. Okay, so our locant is really important. We have a prefix that tells us what are our substituents. So just like how we can name alkyl chains and how we can name different functional groups, the prefix tells us what is attached at that position. The parent chain is something that we are going to be focusing on extensively. The parent chain tells us how many carbons. And finally, we have a suffix that tells us what is the primary functional group. Thankfully, we won't have to worry too much about our suffixes to start off. But this is how compounds are named systematically. And this is the naming format we're going to use for every single compound we encounter. And the most important skill that you need, and this is the best source of trick questions in nomenclature, is making sure you can tell me how many carbons are in our parent chain. And that's what we're going to focus on right now. So, your goal for the parent chain, your goal is to find the longest carbon chain that we call the parent chain. If 2 chains have the same number of carbons, you choose the chain with the most branches. Okay, let's show this method. Your goal is to count from left to right or right to left in your molecule and find the longest contiguous chain of carbons. So for example, in this compound, we can count 1, 2, 3, 4, 5, 6. So that's counting method number 1. Let's look at counting method number 2. 1, 2, 3, 4, 5. Okay, I have 2 ways of counting out my number of carbons. What has more carbons? What's the longest chain? A 5-carbon chain or a 6-carbon chain? 6. So we name it as if it's a 6-carbon chain, and 6 carbons is known as a hexane chain. Hex for 6. Okay, let's try another example. I'm going to try one method of counting. 1, 2, 3, 4, 5, 6, 7. Let's do another color and let's count in another direction. So we can do 1, 2, 3, 4, 5. That's no dice. Is there any other longer chain that you can see? You may have to count across multiple different ways, but the longest chain, what's the most carbons contiguously connected? 7. So we name the prefix for 7 is hept. So this is named as a substituted heptane chain, which has 7 carbons. Does that make sense? Okay, you're always looking for the longest contiguous chain of carbons. So I'm going to get us started on these examples, and I'm going to show you how I solve these problems. So I'm going to start with the structure on our far left. I'm going to show you how I like to count things and how I like to assign the longest chain. So 1, 2, 3, 4, 5. Okay, that's my first attempt. Not the best one, but so be it. 1, 2, 3, 4, 5, 6. Lo and behold, my longest carbon chain has how many carbons? 6. So it's 6 carbons. So 6 carbons, I'd call this a hexane chain. And the reason why I encourage you to put the numbers when you're figuring out the longest chain is you can use these numbers later on for the next part of nomenclature. So you might as well leave the groundwork for you. Okay, I want you now to break into groups and tackle these next 2 problems, and we'll come together to discuss in a few minutes. Everything going okay? Yep, exactly right. Everything going okay? Mhm. Yep. Yep. So what do we call a 7-carbon chain? Yep. Heptane. Yep. Mhm. That's good so far. So let's now come together to discuss. So let's assign our carbon atom numbers and let's try to figure out the longest carbon chain. So starting, counting from left to right, 1, 2, 3, 4, 5, 6, 7. Let me count using a slightly different pen color. 1, 2, 3, 4, 5, 6. So what is our longest carbon chain? 7. So what do we call a 7-carbon chain? Heptane. So we name this carbon chain as if it's a heptane chain because it's 7 carbons. Finally, let's look at the structure on the right. Let's count. So the first method is 1, 2, 3, 4, 5, 6, 7, 8 carbons. There may be a better method of counting. Let's try one more. 1, 2, 3, 4, 5, 6, 7, 8. But there's actually a third method of counting through this carbon chain, which involves counting from left to, I guess you can say left to left in a way. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you really want to investigate every possible way of counting, not just left to right and right to left, but any way that gets you from one end of the chain to the other. So since this is a 9-carbon chain, what do we call it? Nonane. Yes, so this is a nonane chain or nonane chain. Does that make sense to everyone? Okay. Now, this is really important because if you mess up your main carbon chain, your entire name will be incorrect. So let's now keep going and let's talk a little bit about identifying and naming the longest carbon chain in these slightly more tricky examples. So what I'm going to do is I'm going to give you a few minutes to work on these and then we'll come together as a group to discuss. And I have for your reference all of the major carbon chains that you'll encounter in this class and their names. Everything going on? It's good. Everything going on? Let's see, let's change the first one. Yep, exactly. Yep, looks good. Yep, 7, 7. Yep, looks good. Everything is going okay? Yep, that's good. So, I saw a lot of reasonable responses for these questions. Let's now come together and let's discuss all the potential ways of numbering these compounds. And just as a hint to all of you, one of the faster tricks that I use a little bit like as like passive computing for these sort of problems is I always keep an eye out for my longest alkyl chain. Your longest alkyl chains will give you a guideline for where to generate the longest main chain. So for example, I'm going to start counting from this topmost carbon because it's in one of the longest alkyl chain, a propyl chain. And I'm going to try to count from one end of my molecule to another, going through as many of my longest chains as possible. So this gives us an 8-carbon chain. Did anyone find a longer chain than an 8-carbon chain? Nope. The second most longest chain is 7. I always like to think about and look for the longest chains in my molecule because those give me a sign for where to find the parent chain. So this is 8. And what do we call an 8-carbon chain? It's octane. Yep, exactly. So this is an octane main chain. Does that make sense to everyone? You can count not just from left to right and right to left, but from any end of your chain to any second end of the chain. Okay, let's consider the next 2. The next 2 are relatively less tricky. So counting 1, 2, 3, 4. And when I'm at this juncture, carbon 4, I can choose to count to the chain on the right or the chain on the left. So let's think a little bit about this. So let's write out chain number 1, 5, 6, 7. And let's write out chain number 2. Okay, even though we have 2 identical carbon chain lengths, what is our tiebreaker? What are we supposed to pick? The chain with the most branches, yes. So which chain, the chain in red or the chain in blue, has the most alkyl groups attached to the chain, the most branches? Which one? What was that? The red, yep. The red chain, let's highlight and let's label, has a total of 1, 2, 3 different alkyl groups attached. The blue chain, by comparison, has a total of 1, 2 alkyl chains. Because the red chain has more branching side chains, more alkyl chains attached, we choose the red chain preferentially. So the red chain wins out. And it's a 7-carbon chain that we call it a heptane chain. So the amount of alkyl groups attached is your tiebreaker.
Can you repeat that one?
Yes. So the red chain has 3 branching groups. The blue chain only has 2. The more branching your chain has, the more preferred it is for naming. So you always pick the chain with the most branch. Does that make sense? Yes. Yes.
So here we're saying red heptane, right?
Yes.
So what would the red stand for in the normal, like, because otherwise, how do I know heptane from heptane?
So what we're going to do next is we're going to take these numbers and use them to assign the position of each of these alkyl chains. So knowing that we're counting using the red numbering convention will be used later on to say, oh, this methyl is at carbon 3. And so you can differentiate what carbon chain is being referred to, even if they're the same length, because the numbers that indicate the location of each substituent will be different. Does that make sense? Perfect. So the precursor, and the reason why we're deciding between 2 heptane chains is we're going to use these numbers to tell us the exact position of each substituent. And we need this numbering system to fully name our compound. Okay, let's keep going now, and let's try to figure out the longest parent chain. There's only one longest chain in this case. Whoops, one moment. There's only one longest chain in this case. It is a total of 7 carbons, so we call this a heptane chain. Now, there's one other prefix that refers to a constitutional isomer of an alkyl chain. And these are especially important, and we'll talk about them a lot in chapter 4. We call these groups Cyclo Alkanes. So as their name implies, they're alkyl chains arranged in a ring or cyclic structure. Now, an important rule for naming is that the Cyclo Alkane is generally the parent chain. Generally the parent chain if the attached carbon chain has less carbons. So instead of propane, since it's cyclic, we call it cyclopropane. Instead of butane, it's instance, it's cyclic cyclobutane. Okay, now we're going to get into a very, very long set of rules that tell you how do I name my substituents. And even though it's a lot of words, it's very simple in practice if you're good with the numbering method. So carbons in the main chain are numbered in sequence. And in general, you want your substituents to have the lowest numbers. Okay, so our goal is to minimize our locant numbers. Substituents are then identified and numbered. Okay, we're going to write each of the branches and substituents in alphabetical order before the base and stem name, which is our longest chain. So we're already pretty good at naming the longest chain, right? We did that a lot in the earlier examples, right? So we have that down. Now, the way that we indicate the position of each of our branches is by prefixing its name with the carbon number that that chain is attached to. So that's why we numbered our carbons when we were figuring out the longest chain. So we can use those carbon numbers to indicate the position of our alkyl groups. Does that make sense? Okay. Now, we'll come back to these more nitpicky rules later on. The one thing that I do want you to know is that if a branch or substituent occurs more than once, we're going to prefix the name with di, tri, or tetra to indicate the number of that substituent. Okay. Now, let's take a look at the following example, and let's talk about some common mistakes that are made and how we go about, once we have the longest chain, numbering the carbons in our chain. Okay, so taking a look at this molecule, we've identified the longest chain to be 9 carbons. This is 9 carbons, which is nonane. Now, even though we have 2 potential nonane chains to work with, what I want us now to pay attention to are our carbon numbers. So when we talked about our substituents, do we want large or small carbon numbers? Small. You want the smallest possible set of carbon numbers, and you want the smallest possible carbon number, period. So let's look at our carbon numbers. So in this case, we have a substituent at the 3 position, the 4 position, and the 7 position. So these are our substituent numbers. Does that make sense? Looking at the structure on the right, which is the same structure but with a different numbering method, we have substituents at the 3 position, the 6 position, and the 7 position. So the first thing you're going to compare is your first number. You want the smallest number overall, right? They both have 3, so it's a tie, right? We then move to our next carbon number. And if we compare 4 and 6, which numbering method gives us the smallest carbon number? 4, exactly. Does that make sense? So you count in order and you want the smallest sets of numbers and the smallest number overall. Okay. So let's name each of our alkyl chains. So what do we call a 2-carbon chain? 2 carbons. What was that? Ethyl, yes. So 2 carbons is known as an ethyl chain. So this would be 3 for our location, followed by ethyl. Does that make sense? You write the carbon location, then a dash, and then the name of the substituent or alkyl chain at that position. Okay. What do we call a 1-carbon chain? methyl. So this would be 3-ethyl. Now, so this would be 4-methyl. Finally, at carbon 7, do we have another methyl group? Yes. Now, instead of saying 4-methyl 7-methyl, we'll instead say 4-7. And since we have how many methyl groups? How many methyl groups do we have? 2. So this would be 4,7 dimethyl. Now, since we're following alphabetical order, if we want to follow alphabetical order here, if we compare E and D, what is first? D. So this would be 4,7 dimethyl, 3-ethyl nonane, just as our preliminary name. There are a few more rules that we need to consider, but this is the preliminary way that you assign both the carbon number and the name of each substituent and how you order each substituent when writing out the full name. Yes?
So this would be kind of background to how that one kind of we did in the lab last
Yes,
week,
is name. Exactly.
and that was 4 on 2.
Yes, exactly. The carbon numbers indicate the locations of that specific substituent. Yeah. And we'll talk about how we name more complicated molecules throughout the semester. For now, we're just dealing with alkyl chains. The rules get a little bit more complicated once you have different functional groups. Everyone comfortable so far? Let's keep going then. We have one more example. What I want you to do is, I'm not asking you to name this entire molecule, but what I want you to do is find the longest chain, and I want you to find the smallest possible set of carbon numbers and the smallest overall carbon number. And I want you to name each alkyl chain with carbon numbers as well. So it's a little more complicated than the previous examples, but we have a little bit more time. So always start with your numbering method. Yes. Yes, you can, but it would be 7.
Yeah.
So you're correct in the denied carbon chain. So you want the smallest overall starting number and the smallest set. So like, for example, if you have a way of naming that starts with a 1, it would be preferred over naming that starts with 2, 3, etc. Does that make sense? Good. Everything going okay? Everything going okay? Yep, looks good. There may be a longer chain. Oh, try counting from this carbon to here. Yes. Yes. Yes, it is. And the reason why you don't count in the opposite direction is because it will give you a larger set of numbers. Does that make sense? Everything going okay? Yep. And then when you write your numbering, try also writing your numbers counting in the opposite direction along that same chain. And that's how you can compare the potential carbon numbers. Yes, exactly. On the same chain. On the same chain. Everything going. And then let's have the second. Try to name the substituent with its carbon. Okay. Everything going okay? Yeah, exactly. Everything going okay? And I always like to personally circle the longest chain to make it easier for me to see. Yep, exactly. So you look at your numbers, and whichever one gives you the smallest number with the first substituent is preferred. Yeah, so there's 3 and 4. So let's start. 3. Yeah, so you see counting from this end to this. Yes, exactly. Yes, exactly. Everything's going okay?
Yeah, well, this is the longest, right?
Yes.
And so jumping up in here, you would be counting both of these, so this would be at me.
It would just be method because it's
Oh,
just
my
one. But there's another way to count in the opposite direction, and they give you smaller numbers. So if you count, instead of going from left to right, try counting from right to left and see if you get smaller numbers.
Not so much the carbon
It's
length,
the same
but-
carbon chain, but the numbering.
Oh, I see what you're saying.
So let's talk about this example. So everyone is very quick to point out, remember my rule, what are we looking for when we're looking for the longest chain? We're looking for the longest, like what's a good, what trick did I show you? The longest chain typically is indicated by the location of the longest alkyl chains, right? So I see this butyl chain and I'm immediately drawn to want to count towards it. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, that's a long chain. Are there any chains longer than 10 carbons? No. But we're not done counting. In addition to counting from left to right, or from one side of the chain to the other, you also want to write a set of numbers going in the opposite direction because we want to minimize our carbon locant numbers. So then, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, what I want us to pay special attention to is what number do we assign to our first branch? So in red, what's the first number assigned to a branch? 3. In our second compound, what is the first number assigned to our branch? 4. Now, what is smaller, 3 or 4? 3. Since 3 is smaller, we are going to use the red numbering method because it gives us the smallest possible carbon locant numbers. So then, so this is 10 carbons. So this is a decane chain. And now in terms of our substituents, at the 3 position, we have what? What do we call that 1 carbon substituent? Methyl. So this would be 3-methyl. At the 4 position, what do we have? Ethyl. Yep. Because does the 4 have a substituent attached to it?
Oh, yeah, I'm
Yeah.
thinking the blue.
Yeah. Yes.
So when picking, I got a little bit of a different idea because I counted the other groups and I got this one that you chose has 6 and 7 for the other ones, and the other one had 5 and 4. So I wasn't sure how we're supposed to pick.
You start with the chain that has the smallest overall number,
Okay.
and then you go to the smallest next
Next.
number in the chain.
Okay.
Yes, you want to minimize your numbers overall. And that's a very good question. Okay, so what's the next substituent? After carbon 4, what's the next substituent? 6. And what's at the 6th position? Propyl, yep. And then finally, what's at the 7th position? Methyl. Okay, and we won't worry about combining this together into a formal name yet. I just want you to get your carbon locant numbers down. So we'll continue on this in our lecture and lab, and we'll meet back together for our lecture and lab in approximately 7 to 8 minutes. Yes.
But it's easier to take notes in here. Are we able to just stay in here instead of going to the lab?
Oh.
The chairs are so awkward to take notes.
Oh, let me check. What we can do is we can take a short break. Okay, so now that everyone is back from their break, let's now take a look at another carbon chain. Let's focus on assigning the smallest possible set of numbers and creating the longest possible carbon chain. So let's take a look at the following compound, and let's try to develop the locant, the name of each substituent, and the name of the longest carbon chain. So we're slowly developing the pieces necessary to name these compounds. So that's is there a more branched chain of the same length? Count 7, 8, and then it's more branched, right? And then from there, it's which way of counting is the smallest. That's branched. The longest chain. Well, longest first, then most branched, then smallest. Oh, so that one is on the right track, but there's a way of counting where you do a smallest, smaller set of the track. Everything going okay? Yeah. And then so the chain designated is correct. What I would consider is
No, I'm just trying to figure out
oh,
the branches.
the branches. Okay. Try thinking of how your numbers will look like and counting from right to left. Everything going okay? Okay, so which set is the smallest overall? So in this one, you have 2 and 4, for example. Compared to 2 and 3. So that's smaller set. Yes, exactly. Yes, exactly. Everything going okay? So for the 9, there's an even more branch chain you can draw. Yes, exactly. Because it has this group on the side. So we have one more, we have another on the side. Yes. Yes, and now you have one more branch. Does that make sense?
Oh, yeah, got it.
So let's talk about this one. This one looks very innocuous at first glance, but it's actually somewhat tricky. So let's think of many different ways of counting. I'm aiming for the longest chain with the most branching. And the way to get the most branching is to try and count through as many branched alkyl groups as possible. So counting 1, 2, 3, 4, 5, 6, 7, 8, 9. This was the common highly branched chain that I saw from many students. Is there a more branched chain that we could potentially make? Nope. But what we do need to consider is that there's more than one direction to count across the chain. So even though this is the longest chain, we went from left to right. We also need to make a set of numbers from right to left. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So now what we're going to do is I'm going to write out the numbers of substituents in each of these chains. So in red, what carbons have substituents? What carbons have substituents? Let's write down those numbers. 2, 3, 5, 6, and then 8. Okay, let's write out each of our substituents in our other color. So we have 2, then what's the next number? 4, yep. What's the next number? 5. What's the next number? 7. What's the next number? 8. Okay, perfect. So we have 2, 4, 5, 7, 8. Okay, so with that said, where do we see the smallest numbers from start to finish? In red or in black? In red. And the key thing is, once you see this 3 and 4 difference, the red counting method wins as the smaller numbers. You're not looking at your overall set of numbers, you're looking at your smallest numbers counting from the start to the end of the chain. So then, using our methods in red, so this is a 9-carbon chain, so this is a no-name chain, and so at position 2, what do we call that substituent? What do we call that substituent? Methyl. So this is 2-methyl. At position 3, what do we call that 2-carbon chain? Ethyl. Yep. What about at carbon 5? What do we call that 2-carbon chain? Ethyl. Yep. At carbon 6, what do we have? Methyl. Yep. And at carbon 8, what do we have? Methyl. Okay. Okay, now of course we wouldn't individually put, we wouldn't say it like 2-methyl, 6-methyl, 8-methyl. We'd write this as 2, 6, 8, and since we have 3 methyls, what would we call it? Tri. So this would be 2, 6, 8 trimethyl, and instead of 3, 5 ethyl, it would be 3, 5 diethyl. Exactly. We're not going to worry yet about how we arrange these substituent names. That's what we'll cover momentarily. We're just making sure we can assign our locant numbers correctly. Any questions on this example? Okay, let's keep going then. So our goal, and really practice does make perfect, our goal is to identify and name all substituents in the following molecule, and then name the parent chain. So there are 2 examples to work with on this page. Let me zoom out so we can see both of them. And let's try to work on both of these examples, and we'll come together to discuss in about 5 minutes. Don't be shy to share your ideas with your partner as well. Everything going okay? Mm-hmm. Everything going okay? Everything going okay? The rules make sense so far? Yeah, okay. Looks good. I have to figure out a counting method, but with the number that you have would be the small substituent. Yeah, that looks good. Let's try tackling these. Everything going. Yes, the number looks good. So is there a potential longer way of counting? Is there a potential longer chain? So if we compare this 3-carbon chain to 4, if you count this way, if you're very close. Everything going okay? Yep, exactly right. And which numbers, green or blue, are preferred? Yep, exactly. Mhm. Everything going okay? Yep. Yep. That looks good. So you want the smallest set of numbers with the most branching. So comparing these two, the purple would be preferred. Yep, exactly. Oh, I'll be right over. Yep.
Okay.
But I would think because either way you have a two numbers.
Okay.
That's the beauty of that system. Everything going okay? What was it? What's it? Carbon 2? Oh, but what's attached to carbon 2? Yeah. Yep, so it'd be 2, right? So I saw a lot of reasonable answers. In terms of counting, my first method of counting is to count across our longest alkyl chains. So when I'm at carbon 5, what I'm thinking to myself is, what is the longest chain attached to carbon 5? So I have either a propyl or a butyl group, and what has more carbons? Butyl. So let's keep counting. 6, 7, 8, 9. Let's do an alternative method of counting, counting in the opposite direction just to compare our numbers. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So what method of counting gives us the smallest set of numbers and the smallest absolute number? Black. Yep. That gives us at carbon 2. What do we have at carbon 2? What group do we have? Methyl. So this would be 2-methyl. And at carbon 5, we have what substituent? Propyl. Yep. And then finally, since this is a 9-carbon chain, what do we call 9-carbon chains? Nonane. Yes. Okay, perfect. Let's now move to the next example. So let's write out all of our possible methods of counting. Let's write out all of our possible methods of counting. I'm going to walk down the chain, and each time I reach a branch, I'm going to pick the longest chain in that branch. So 1, 2, 3, 4, 5, 6. Okay, I have a choice between a set of 2-carbon chains. If I have a choice, do I pick the more branched or the least branched? More branched. So 7, 8. Perfect. Okay. So from here, I'm going to write out my second set of numbering. 1, 2, 3, 4, 5, 6, 7, 8. And which set? The set of counting in black or red gives us the smallest overall set of numbers. Red. Yep, exactly right. So let's just write that out for comparison. Let's write that out for comparison. So in the counting method on black, we have carbons 2, 6, and 7 containing substituents. For the counting method in red, we have carbons 2, 3, and 7. Now, what is the smallest set of numbers? 3 or 6? What's smaller? 3. So then we name using the red counting method. So at carbon 2, we have what substituent? Methyl, yep. At carbon 3, we have what substituent? 2 carbons, which is ethyl. At carbon 7, we have what substituent? Methyl. So we would write this as 2,7-dimethyl. Okay, perfect. And since this is an 8-carbon chain, what do we call this? Octane. So 8 carbons, that tells us we have an octane chain. Perfect, perfect. Let's now continue on with this. So when you're naming complex substituents, what you're going, so by complex, I mean heavily branched substituents, what you're going to do is you're going to place numbers on the substituent starting from the carbon attached to the main chain and moving away from the main chain. Okay, so to give you an example, looking at the following molecule, you have this really heavily branched substituent that can't be named using any of our common abbreviations. Like this doesn't match any of the known like tert-butyl, isobutyl, sec-butyl, etc. examples. The connectivity doesn't match. So what we're going to do is we're going to put a dot on the carbon attached to the main chain. And I just always like to draw a little dividing line just to show me this is a side chain that's attached to my main chain. Then, just like I do for counting my carbon locants, I put the number 1 assigned to the carbon attached to the main chain. I then count in a way that gives me the longest carbon side chain. Does that make sense? So it's even easier than when you're counting locants when you have the main chain, because you always know what carbon 1 is going to be. It's the carbon that's attached to what? Main chain, exactly. Then you'll name the substituents on the side chain and number the side chain substituent based on their carbon number. If the substituent has a common name, make sure you use the IUPAC name. So let's take a look at the following example. Let's take a look at the following example. So we have 6,2-methylbutyl undecane. So looking at our counting methods, we count 1, 2, 3, 4, 5, 6. So this entire little subchain is found at carbon 6, okay? Now let's dissect this side chain and let's apply some numbering. So it's a 4-carbon side chain. What do we call a 4-carbon side chain? Butyl. So then, 4 carbons tells us that we have a butyl side chain. And are there any substituents attached to this butyl chain? Yes. At what carbon? 2. So we'd call this 2-methyl butyl, because it's a butyl chain with a methyl at the 2 position. Does that make sense? Okay, so counting, this entire substituent is at carbon 6. That's why it has the 6 label. We then put in parentheses and we dissect this side chain. Carbon. Oh, so if you keep going, 7, 8, 9, 10, 11, 1, 2, 3, both methods of counting give you the same number. Yeah, but the 6 is what?
What I was talking about is where you started with the one on the side.
Yes. So when you're dealing with side chains, the carbon attached to the side chain always gets the number 1 without fail. So you never have to consider 2 sets of numbers. The carbon attached to the side chain always, so carbon attached to the main chain always gets the number 1.
Yeah, I get that.
Yeah.
No, what I'm saying is the bottom chain, right?
Mhm.
Without the side.
Yes,
chain,
actually,
you
we
have
can-
the one
we can-
line.
We can show that. Let me show you. So counting from left to right. we end up with the same carbon 6 for our side chain substituent. The 1, 2, 3, 4 is the numbering method for the side chain. Does that make sense?
Yeah.
Okay.
So it doesn't really matter for this one.
Yes.
Where you start. You can
Yes.
start from the end, or you can
Yes.
start.
But we, just to show, in both black and red, both methods of counting give you the same locant for that side chain. The focus on this one is how do we name these complex side chains? You write out, starting from number 1, attach the carbon, attach the main chain. So carbon 1 is always fixed. You assign your remaining carbon numbers. You write the locant for each substituent. So in this case, 2-methyl, and this entire side chain has 4 carbons. 4 carbons, that tells us what? Butyl, exactly. So this is 2-methyl, 2-butyl. Does that make sense? It's almost recursive in a way. Thankfully, the majority of these complex side chains you'll see have a common name. That's why I showed you all the common names. For example, tert-butyl, isobutyl, isopropyl, and we'll be using those in this next section. Does that make sense? Okay, so let's start applying. So I have a summary table of the common named substituents where R is our parent chain. We've all covered these before. I just want you to be familiar with them because you're going to be using these names a lot. So your isopropyl, the R group is at carbon number 2. In isobutyl, we have a carbon arranged and a carbon attached at carbon number 2, and our main chain is at carbon number 1. T-butyl, if you look at the shape of T-butyl, it almost looks exactly like a T. Does everyone see how it looks a little bit like a T or a cross or an X? So that's how I like to remember it. And the main chain is attached at the tertiary carbon. Butyl, as its name implies, secondary. The R chain is attached at carbon number 2. Now let's take a look at pentyl chains. These pentyl chain isomers are quite interesting. You have N-pentyl, which is just your normal 5-carbon chain. In isopentyl, so this iso group is this 3. The iso group is best identified by this 4-carbon arrangement of atoms that looks a little bit like a Y. Does everyone see that shape? That's shared among all iso prefix constitutional isomers. For neopentyl, a neopentyl group, you have your T-butyl-like substituent, and the R group is attached to one of the T-butyl primary carbons. So the R group is attached to, in this case, a secondary carbon. So instead of being directly attached to your T-butyl-like substituent, it's moved 1 carbon over. That's why it's called neopentyl. So these are the, yes? Because it has the R group and the T-butyl chain. So it has 2 things total.
So are we taking that R, the first thing on that R as a carbon? Because I thought it had to be a carbon-carbon bond.
Yeah, so in general, R for this chapter is going to be a carbon chain.
Okay.
Yeah, but it won't always be. Yes.
So what does the butyl and pentyl refer to specifically?
It refers to the number of carbons. So pentyl is 5.
Okay.
Butyl is 4. And it refers to the number of carbons in our side chain. Yes.
So I'm just seeing patterns that I-pentyl and I-butyl both have that Y shape.
Yes.
And then the T-butyl and the neopentyl also have that T shape.
Yes. And the difference between T-butyl and neopentyl is where the R chain is located. So whether the main chain is located specifically on your tertiary carbon, in this case, or your newly formed quaternary carbon, or if it's on the primary, which would turn into a secondary
So then the S dual with
Yes.
the pattern there for the R in the upright position.
carbon. We don't worry about the relative position, because that's more concerned with stereochemistry, but the key thing that's important is on carbon number 2. So it's moved 1 carbon over. So the connectivity is slightly different from this linear chain. Does that make sense? Perfect. So the best way to incorporate each of these common chains is to focus on naming each of these common chains. So let's start off with a typical example. I'd like you to identify each substituent and then indicate the systematic and IUPAC name for each substituent, and then we're going to name the longest chain. So I'm going to help us out, and I'm going to start us off for this one. So I'm going to assign 2 sets of carbon numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that's our longest carbon chain with 11 carbons. Let's try both directions of counting. Okay, so both of these chains have 11 carbons to their name. Which counting method gives us the smallest set of numbers? The counting method in black or the counting method in red? Which count? Black, yep. So we'll count using that method. Now, looking at the following function, looking at the following alkyl chain, we have 3 carbons and our main chain is attached to carbon number 2. What do we call that chain? It's 3 carbons, the main chain's attached to carbon 2. So for propyl, we don't use the SEEK abbreviation, but, oh, isopropyl, yeah. So propyl doesn't have the SEEK notation, you just call it isopropyl. So this substituent here, so this would be 4 isopropyl, but you are on the right track here. On carbon number 7, we have a chain where our main chain is attached to carbon 2. So it's 4 carbons and our main chain is attached to 2. Yes?
So the primary for the chain will be the one that is closest to the chain? Or?
Yes, so the carbon attached directly to the main chain gets a 1.
Oh, that's all right.
Yes. So for example, isopropyl would also be named 1-methyl. Could also be named 1-methyl ethyl. But that's a little bit egregious. Yes.
What's the number 2 you're referring to?
So I'm using so when counting, if I pretend that we have a normal isopropyl chain, I like to think of it as 1, carbon number 2, carbon number 3 in a normal propyl chain, and that way I can help to recognize patterns. That's not the formal numbering method, but it's the way I help to remember that it's isopropyl. Yeah. So, likewise, looking at the connectivity of our main chain, this is 4 carbons, so this is a butyl-like chain. But since our main chain is not attached to the first carbon, what do we call this? What do we call this branched group? Seek butyl. Yep. This would be seek butyl. Because in our theoretical butyl chain, it's attached to the second carbon instead of the first. Does that make sense? Yes. Yes. But for the propyl, there's no SEEK abbreviation. It's only isopropyl if it's attached to carbon number 2. And the reason why the SEEK butyl and isobutyl are slightly different naming conventions has to do with the fact is that for isobutyl, you have your same iso arrangement of atoms, but your R group is attached to the primary carbon, or carbon 1, counting along that theoretical chain. The Seq naming convention explicitly indicates that your main chain is attached at the second carbon. Does that make sense? Perfect. So this would be 4 isopropyl, 7 Seq butyl, and since this is an 11 carbon chain, what do we name it as? Undecane, yeah. So it's 11 carbons, so this is undecane. Does this example make sense to everyone? And whenever you're stuck, don't be shy to refer to the table, but by the end of this chapter, and eventually when the next exam comes around, you want to be able to name each of these branched side chains without having a reference table. That's your goal. So I'm going to let you loose on the following example. It's a little more simple, but I want you to be able to recognize all of the common branched side chains and name. Yes.
So the prefixes version, so like iso.
So just as a refresher, yeah. So the iso prefix tells us that we have a 3-carbon arrangement of atoms with a carbon or a main chain attached to carbon 2. The iso prefix is utilized, but when we get to the butyl chain, to designate the location of our main chain, we isobutyl, the main chain's attached to carbon 1, and we have this 3-carbon arrangement of atoms. When we have a Seq butyl chain, the main chain is attached to carbon number 2, and it looks exactly like an N-butyl chain in terms of connectivity. Yeah. Does that make sense? And the reason why we don't call isopropyl Seq propyl is because then the convention for the iso name has to do with this specific 3-carbon arrangement of atoms. And the Seq abbreviation indicates the location of the main chain. Yeah. And you only need to use the Seq abbreviation if you have a linear chain with your main chain on a different position. Yes?
So to double check on how we count how many carbons are attached, you're counting from like where that arrow is?
So to help recognize the iso, I like to count from left to right and just label my carbons as carbon 1, 2, and 3. Okay. This isn't the actual numbering that you'd use if you're using systematic numbering, but it's my way of helping to recognize each of these different side chains more efficiently.
Okay, and then when you're counting butyl like that, the T butyl, how do you count that?
Oh, how do I count that one? So it's mainly the fact that the tert butyl carbon is the most substituted carbon. It's tertiary. So if our main chain is attached to the tertiary carbon and we end up with a quaternary carbon, that's a key signpost you have a T butyl group. If we compare T butyl to neopentyl, we still have this T butyl-like arrangement. For the neopentyl, we have 1 additional carbon, and our main chain is attached to the primary, which becomes a secondary carbon. Yeah. So the neo abbreviation tells us instead of having a normal T butyl group, we instead have our main chain at another carbon position. Does that make sense? Okay. And there are many different prefixes for common name chains. These are just the ones that you'll see most often. If you're stuck and you need to name something, you can always just break down and give me the systematic name, and I'd give you credit for it. But it's far more common for these side chains to use the common name. Does that make sense? Perfect. So let's take a look at the following molecule, and let's try to name it using IUPAC naming convention. Yeah, and you can abbreviate terbutyl as just T. Yeah. Yep. Yep. Everything going okay? Yep. Perfect. That's good. So what do we call that? But where is our main chain located? What is our main chain attached to? So it would be look. Yep, exactly. So it's attached to this carbon, which is highly sensitive, and has fitted to 4 carbon chain. Yes, and the fact that it's a 4 carbon chain. No, 4 carbon side chain. And then the center. Yep, exactly. Yep, but oh, you miscounted. It should be 7, but otherwise it's good. Okay. I see a lot of reasonable answers. First things first, would someone like to tell me what do we call this substituent? We have our main chain attached to our tertiary carbon, making it a quaternary carbon. What do we call this? T-butyl. Yep. So let's add some numbers to this. 1, 2, 3, 4, 5, 6, 7. Okay. No matter what direction we count, both in black and in red, we end up with the same set of numbers. So there's no preference for which one we should use. So since we have a 7 carbon chain, what do we call that? Heptane. So then this would be 4 T-butyl heptane. Does that make sense? Okay. For those of you who happen to follow the download link that I gave at the beginning of the semester for Marvin Sketch, it has a wonderful program that allows you, given any structure, it will spit out the IUPAC name for you. So this is a great way to just generate your own problem sets for nomenclature. You just put the structure in Marvin Sketch and then try to name it, and then you hit the structure to name function and it will pop out the name for you to check your work. Any other questions on this example, or should we keep going? Okay, let's keep going then. So let's talk now about how do we assemble the name? How do we put the name together? Okay, so first and foremost, you number your carbons in sequence, and you want your substituents to have the lowest numbers. We name our substituents, okay? Perfect. Now, part 3 is new. How do we arrange each of our substituent names properly? So we arrange each of the branches and substituents in alphabetical order before the base stem name. Okay? Perfect. So the prefixes cyclo, iso, and neo are part of the group name and are alphabetized. So let's put a star next to these. These are the ones that we need to remember. The prefixes di, tri, tetra, tert, seq, etc., you're ignoring them. So I'm just going to put a circle through them. Okay? So the only prefixes that you care about for alphabetizing are cyclo, iso, and neo. If it's not one of those 3, you do not care about the prefix. You use the base name. Does that make sense? So let's just do a test here. Let's just do a test. So for example, if I have cyclohexyl, what letter do I care about for alphabetizing? C. So cyclohexyl, cyclo's on the list. We care about the C as our alphabetical ordering. If I have T-butyl, let me write this in red so that way we can tell the difference. So T-butyl, do I care about this tert prefix? No. So then what letter do I care about for abbreviations? B. Yeah. There we go. This is really important because your substituents need to be in alphabetical order. So it's not numerical, it's alphabetical. Okay. Now, if a substituent occurs more than once, you prefix the name with di, tri, or tetra, and you list the number of carbon branches for each substituent with a separate number for each occurrence. Okay, so in terms of guiding methods, in terms of rules of thumb to look out for, you want to make sure you're choosing a numbering method that gives you the smallest starting number. So for example, counting from left to right, our substituents are at carbons 2, 5, and 5. We don't care about the smallest overall set of numbers. We want the smallest starting number. That's it. So we have 2,5,5 trimethyl. That wins out over the alternative counting method. That would give us substituents at carbon 3, and carbon 6. So even though we have a smaller set of numbers on the right, we want the smallest absolute number. So 2 wins out over 3. Does that make sense? Yes.
And then if, for instance, this first number is the same, that's when you would look at the second one?
Yes.
Okay.
You keep going down and you compare each numbers for the next carbon substituent in the chain. Yeah. Okay, let's talk about a few more rules. So if there's a tie, and conveniently enough, I have it right here. If there's a tie, the second number should be as small as possible. So in this case, if we count from left to right in purple, we end up with substituents at carbons 2, 3, and 6. Let's compare to if we counted from left to right. Let's compare. 1, 2, 3, 4, whoops. 5, 6, 7. Okay? In this case, we end up with substituents at carbons 2, 5, and 6. So then, there's a tie for 2. There's a tie for our first carbon, right? What about for our second carbon? If we compare 3 and 5, what's smaller? 3. So that's why 2, 3, 6 trimethyl wins out. Does that make sense? Okay, so you keep going down the chain, you keep looking at the next carbon chain, and you want the smallest number. That's it. Finally, if for some reason you end up with a molecule that happens to have the same numbering convention, if there's a tie between your locant numbers, you want to assign the lowest number to the substituent that is first in alphabetical order. So if we compare 4-ethyl 5-methyl to 5-ethyl 4-methyl, what comes first? E or M? What wins? E. So then we put our smallest number in front of ethyl. Does that make sense? And I know these rules may seem very nitpicky and a drudge to go through, but I guarantee all of these are mistakes that are seen time and time again when naming compounds, and naming are the easiest points to get on the ACS because it's just being familiar with the rules. Okay. This rule also applies to Cyclo Alkanes. The only issue for Cyclo Alkanes is that when you choose your counting methods, instead of counting from left to right or right to left, you count clockwise and counterclockwise. So in the first example, we can choose to count starting at this as carbon 1. We can pick whatever carbon we want as carbon 1 for our cycloalkyl chain, but if we want to minimize the numbers for all of our substituents, we want the most substituents to be at carbon 1. So then that's why we put carbon 1 on the carbon containing 2 methyl groups rather than on the carbon containing just a single methyl group. Does that make sense to everyone? So as you count in a way that gives you the most substituents with the smallest number. Okay, let's now put this into practice. Let's focus on putting this into practice here. Let's try and name the following compound. Let's try and name the following compound. Let's write the full name, and we'll do this one together. I'm going to write out 2 methods of counting. The first going from left to right. So 6 carbons. The second method going from right to left. Okay, perfect. So we have all of our carbons counted. So looking at the method in purple, we have substituents at carbon 2 and carbon 4. For the counting method in black, what are our carbon numbers? 3 and 5. So what's the smallest set of numbers here? 2 and 4. Okay, so we're going to name our substituents. So it would be 2. What's at carbon 2? Methyl. Okay. Okay, and what's at carbon 4? Ethyl. Okay, now I think, what goes first? Methyl M or ethyl E? Ethyl. So this would be 4 ethyl, 2 methyl, and we have a 6 carbon chain, so what do we call that? Hexane. So this is 4 ethyl, 2 methyl hexane. Does that make sense? Any questions on this? Okay, I'm going to let you loose now on the following example. Be really careful with your numbering and make sure you have the longest chain. If the name looks weird, maybe make sure your numbering is correct. Everything going okay? Okay. Everything going okay? Yeah. Okay. That's an 8 carbon chain. Yep, looks good. Yep. Just try to find a method of counting that gives you the smallest number. So what gives you the smaller set of numbers? Red or black? Oh, red. Yep. Everything going okay? Perfect. Everything going okay? Mm-hmm. And your carbon chain length is 8, right? Yep, looks good. Let's see. Yep, perfect. Exactly right. Yep, exactly. And the ethyl goes before them because the dye is counted. Everything going okay? Okay. Everything going okay? There's an even longer chain if you count this chain all the way up this way. Yep. Everything going okay? Yep, the method of counting looks perfect. So I saw a lot of reasonable answers. So my first question to all of you is our longest chain, does it have 7 or 8 carbons? 8. So counting from left to right, 1, 2, 3, 4, 5, 6, 7, 8. And no, I'm not just cherry picking. I'm going to show you both of the valid ways of counting. and we're going to compare the numbers to figure out what numbering method is preferred. So counting in red, 1, 2, 3, 4, 5, 6, 7, 8. So which counting method gives us substituents with the lowest carbon locant numbers? Flat, yep. So then at carbon 2, we have what? Methyl. Okay, at carbon 2, we have methyl. At carbon 3, we have what? Methyl. Okay, and at carbon number 4, we have what? Ethyl. Yep. Are there any other side chains that we haven't accounted for? Okay, so now what goes first? Ethyl or methyl? Ethyl. So we'd write this as 4-ethyl. And since we have 2 methyl groups, we're going to write this instead of just 2-methyl, 3-methyl, we're going to write it as 2,3-dimethyl. Yep. And then what do we call an 8-carbon chain? Octane. So this is 4-ethyl, 2,3-dimethyl octane. Not too bad, right? Now, since we practice a lot of the pieces, it's a lot easier to put them together. Let's do a few more examples. This is best learned via practice. Like, I can explain to you how to do this time and time again, but until you practice a lot of examples, it's not going to become integrated. So let's focus on naming some relatively gnarly compounds. Let's look at these two. You may have to break out your naming of branch side chains, but don't always reach into that bag until you make sure you have the longest chain identified. So always start by finding the longest chain. Everything going okay? Everything going okay? Let's see. So yep, yep, looks good. And this would be so looking at the, yes, the C prefix is not counted. Only cyclo, iso, and actually, you have the something. So cyclo, iso, and are the ones to consider. Anything going? Is there a longer chain that you can find? No, this branch. Yeah. Yeah. Oh, start. Yep. Everything going okay? Yep. Everything going okay? Everything going okay? Yep. And that butyl chain isn't just a normal butyl chain, since it's attached to carbon 2, as we call it. Sorry. Yep, exactly. Except there are 3 prefixes that are counted out. Cyclo, iso, and neo. Oh, so iso is considered an alphabetical. But is B before I? Yes. Yes. So I'm just stating that you have to consider that because in some cases it doesn't make a difference. Yeah. Everything going on here? So is there a longer chain? So this is 3. Is there a longer chain on this branching point? So you're on the right track. What if you count here all the way around this? Right. Yeah. So I try to find the two longest chains and draw and put them together. Does that make sense? Perfect. Everything going okay? Yes, exactly right. And then in terms of prefixes that are counted alphabetically, iso, neo, and cyclo are counted alphabetically. Seq is not.
Sig is not.
Yes, and you have that if you scroll to the naming rule priority. Oh, it's farther down. Everything going okay? There's an even longer chain. So you count from here to here, you have a 5 carbon chain, and then 3. That gives you a longer 8, longer 9. 5, 6, because B before I. Exactly right. Oh, if you go a little further down.
This right.
Okay. Everything going okay? Let's see. Isobutyl for isopropyl. Yes. Wait. Isopropyl. Yes. Yes. Mm-hmm. Yep. Looks good. Yes. Mm-hmm. Yes. Yes. It's 4 carbons, so it's butyl, but it's not just a normal butyl. Oh, wait, which one are you from? Pre-circle form? On carbon 5, right? So that side chain, it's 4 carbons, it's a butyl, but it's the main chain is attached to carbon 2. So what do we call that? 2. Otherwise, it's like a secondary carbon. So it's tertiary, looks like a T. This is on a secondary carbon, so we call it secondary. Yes, exactly. So let's talk about the first example. I saw a lot of reasonable answers. This one is mainly a test to make sure you know how to count your carbons. So I always like to look at all my different carbon chains, and I like to find the longest chain, right? So I see this giant 4 carbon chain, so I'm going to start counting there. 1, 2, 3, 4, 5, 6, 7, 8, 9. The reason why I took a detour down to this chain, what's longer, 3 or 2? What has more carbons, 2 or 3? 3, right? So you always count through the longest chains. Perfect. Now, just to make sure to show you I'm not just cherry picking and showing you the correct, what? Just to make sure I'm not just cherry picking and showing you the correct answer, what we're going to do is we're going to compare the numbers obtained counting in red versus black. Which counting method gives us the smallest set of numbers? Let's compare. Red. So at the red counting method, we have substituents at the 4 position and the 5 position. So what do we call this substituent? It's a 3 carbon chain with the main chain attached at the second carbon or the secondary carbon. Isopropyl. So this is 4 isopropyl. What about at carbon 5? So at carbon 5, we have a 4 carbon chain with our main chain attached at the secondary carbon. Seq butyl. So this is 4 isopropyl, 5 seq butyl. Remember, we do not count the seq prefix, but we do count the iso prefix. So then what is alphabetically first, I or B? B, yep. So this would be 5 S-butyl 4 isopropyl. And then what is our main chain? 9 carbons. Nonane. Okay. Does that make sense so far? I'm going to now let you loose to continue on with the second structure. And I'll be walking around and checking to see how everyone's doing. And then we'll come together to discuss in a few more. Everything going okay? Yes, so it's the most branched and the longest. Yep, it's yep, exactly right. Yep, looks fine to me. Yep, perfect. Is there a more branched chain? Is there a chain with more information such? Yeah, exactly. Everything going on? And you're very close. Is there a way that we can count and give us a more branched chain? Yes, exactly. Yes. So is there a way of counting that would give you a more branched chain? Yeah. Exactly. Everything going? Yes, looks good. Everything going okay? So it's 3 carbons with a carbon chain.
There's one here.
And that's why we have the table at the start. You want to refer to for the carbon chain. So I saw a lot of reasonable answers for this structure. Now what we're going to do is we're going to take a look and we're going to identify the longest and the most branched chain. So I see the longest chain is this 3 carbon chain right here. And the reason why I choose the top 3 carbon chain over the bottom 3 carbon chain, the top chain, is it more or less branched? More. Okay, so now let's number 1, 2, 3, 4, 5. Now if I had to pick going off of carbon 5, should I count up or down? Which of those chains is more branched? Down. So we have 5, 6. Let's also show the alternative counting method in red. 1, 2, 3, 4, 5, 6, 7. Wait. Oh, that's why I repeated carbon 5 for some reason. It's getting late. My apologies. Okay, here we go. Now, which counting method gives us the smallest set of numbers? The counting method in black or the numbering method in red? Red. Okay, so now let's label each of our carbons that has substituents, and let's name each substituent. So at carbon 2, we have this 1 carbon chain. What do we call that? Methyl. So this would be 2-methyl. At carbon 3, we have a 2-carbon chain. What do we call that? Ethyl. At carbon 4, we have a 3-carbon chain. What do we call a 3-carbon chain? Propyl. And at carbon 5, what do we have? Methyl. Okay, now we are ready. We don't even have to break out our branch substituent naming, right? Now, what goes first? Ethyl, methyl, or propyl? What goes first? Ethyl. So we only have 1 ethyl, so we'll start with 3-ethyl. What's next? Methyl or propyl? M or P? M. And since we have a total of 2 methyl substituents, instead of writing 2-methyl followed by 5-methyl, we write it as 2,5-dimethyl. Exactly right. Yes.
So with that, would we ever write 5, would we write 5 too if that was the order?
No. You
Well,
always
it's
put the
always gonna be-
smallest number first.
Okay.
Yeah. So always, regardless, you always start with the smallest number. With regards to di, tri, tetra, you never write 5 2. You always write 2 5 because you want the smallest number first for a series of substituents. Now, what's our last substituent? Propyl. So we call this 4-propyl. And then finally, since this is a 7-carbon chain, what do we call it? Heptane. So this is 3-ethyl, 2,5-dimethyl, 4-propyl heptane. Does that make sense? I know it's a lot, but once you break it into individual pieces, it becomes a lot easier to start naming these compounds and dissecting how the naming system works.
So the ethyl on the 3 is the top right?
Yeah, so this ethyl is right here.
Yes.
Yep. Any other questions on this example? Okay, let's do a few more. This time, let's look at cycloalkyl groups. Cycloalkyl groups are the main chain only if they have more carbons than your substituent chain. Otherwise, you name the cycloalkyl group just like a substituent. So let's look at the first case where the cycloalkyl group is our main chain. I'm going to start us off here and I'm going to name this first compound. I'm going to pick a numbering method. So let's write out both of our numbering methods. So I can count 1, 2, 3, 4, 5 around the ring, or I can count, let's use purple. 1, 2, 3, 4, 5 around the ring. Now, there's no difference in the numbers, the absolute numbers that I'm getting for each of our carbon locants. So I have to write out and I have to name each of these substituents. That will be the tiebreaker here. So let's see. And this one's more tricky than it lets on. So let's suppose, what do we call this substituent? Method. Okay. And what do we call the following substituent? Isopropyl. And when we look at our rules for what prefixes are included, is iso one of the prefixes that we care about? Is it included for alphabetization? Yes. So then, if we compare I to M, what is first? I. So then, which substituent should we give the smallest number? The methyl, which is last in alphabetical order, or the isopropyl, which is first? Isopropyl, exactly right. So then we would name this as 1-isopropyl, 3-methyl, and then instead of just pentane, since it's in a ring, we call it cyclopentane. Does that make sense? Okay. Now I want you to tackle the exact same, slightly different example and name the following compound. So the compound on the right. So is the C prefix, is it count or not? Let's check the rules. Cycle, iso, C is not. Yep, exactly. Perfect. So then butyl comes before methyl, and that's why it gets the one designation.
Then no count this.
Yep, exactly, because you count counterclockwise, you get there.
Okay, so.
Exactly. Yes.
Does it really matter where dash is? I want dash.
The two needs to be, so you put a dash, number, then another
I guess that makes sense, but I thought it was trying to find this.
Same numbers.
Yeah, I did that too.
Yep, that's exactly right. So for Cyclo Alkane, I think some off the main cyclic ring is side chain. So this so it's a side chain, it's a 4-carbon chain with our main chain attached to carbon 2.
You just look at it normally.
Yeah, and it's at the second carbon, secondary carbon. Yes.
So I think I was just overthinking a little bit on this one.
Yep.
So is that
So what goes first? C,
So-
B, or M?
B? So that means 3.
Yes.
Okay.
Oh, no,
So
it would
does it
be-
mean?
it would be 1 and 2 because you're counting them. So 1, 2, or 1, 2. Oh, so it would be 1, 2.
Over here.
Yep, or 1, 2. Oh, but start putting the 1 right on the carbon. The alkyl is attached.
Oh, okay.
Yep.
Okay, that's
Exactly. And remember, sync isn't counted in alphabetical
Yeah.
order. Only Cyclo, Neo, and not counted as. So the seek is not counted for alphabetical order. Yeah, and it's why it's it's an AL, that's why.
Yes, you just said we start numbering on the side chain, but if there's more than one side chain.
Then you start give you the small set.
Okay.
So let's now talk about this next example. I saw a lot of reasonable answers, so I'm very glad to see that. So let's look at our 2 potential counting methods. We can either do 1, 2, or 1, 2, 3, 4, 5, 6. Okay, so there's a tie between our numbering convention. So now we have to use alphabetical order as our tiebreaker. So what do we call this 4-carbon substituent where the main chain is attached to the second carbon? Butyl or S-butyl. Okay, we can name this 1-carbon side chain, right? What do we call that? Methyl, yep. Now, is the seek prefix counted in alphabetical ordering? No. So then what goes first? What has more alphabetical priority? B or M? B. Okay, so what substituent gets the number 1? The sec-butyl or the methyl? Sec-butyl. Okay, so then this would be, we get 1s-butyl, 2-methyl, and then what do we call a 6-carbon cyclic chain? Instead of hexane, it would be cyclohexane. Exactly right. Perfect. Any questions? Yes.
So when we begin numbering, when it is the cyclo
Yes.
shape, we start numbering on the side chains.
Yes. On the carbon attached to the side chain.
And why do you put cyclo first? Yeah.
What?
And why do you put the cyclo?
You mean cycle? Oh, because it's it's not just a straight chain, it's arranged in a ring. So cyclo alkyl groups, the carbon chain is arranged in a ring. Does that make sense?
Yeah.
Perfect. Yes.
And then, so because cyclohexane is a side group is why it's not alphabetized. Like,
Yes,
if
yes.
it
It's
was
the
a
main
side
chain.
group.
If it was a side group, it would be second after butyl. But it's the main chain, so it's not alphabetized. Think the main chain is always named at the end. Does that make sense? Perfect. Let's do a few more examples. This time, let's look where we have a cycloalkyl substituent. So let's count our carbon chains. So we have 1, 2, 3, 4, 5, 6, 7, 8. Is 8 carbons in our main chain more than the 6 in the cyclohexyl chain? Yes, 8 is more than 6, thankfully. Let's now write an alternative counting arrangement. And my question to all of you is, what color-coded counting arrangement gives us the smallest set of numbers? Yep, exactly right. So now what we're going to do is we're going to name each of our substituents. So what do we call this 6-membered ring? 6-carbon cyclic chain. Cyclo, yep. And then since it's a 6-carbon chain, we call it a cyclohexyl chain.
So the ane is like.
The ane describes main group. YL is used to describe a side chain. Does that make sense? Perfect. So then, what do we have as well? So what carbon number would we assign the cyclohexyl chain? What carbon is the cyclohexane attached to? So this would be 2 cyclohexyl. What about at carbon 4? What's attached at carbon 4? What do we call that group? Ethyl. Yep. So this would be 4-ethyl. What are attached at carbons 5 and 6? Methyl. Exactly right. So then, now, what is first alphabetically? Is the cyclo prefix counted alphabetically? Yes. So what is first? C, E, or M? C. So we write this as 2 cyclohexyl. Okay, what's the next in alphabetical order? Yep, 4-ethyl. Okay, and instead of since we have 2 methyls, what prefix do we use? Dimethyl. Yep, so this would be 5,6-dimethyl. And then since it's an 8-carbon chain, what do we call it? Octane. IUPAC names of organic compounds are quite long. Does this logic make sense? The only thing that's changed is that the cycloalkyl substituent, the cyclo group, is taken into consideration, and the cyclo prefix is included when you're deciding alphabetical order. Yes.
Like, what if we had 2 cyclohexanes and like one had more than the other? Would we,
What do you mean?
like
The species with the more carbons is chosen as the main chain. Yeah, but those typically don't come up. Like for example, if you have a cyclobutyl attached to a cyclohexane chain, yeah, then the cyclohexane would be the main. Yeah. The longest carbon chain wins out as the main chain. So let's put this into practice and let's have you name the following compounds. So take a few moments to work on naming the following compound, and then we'll come together to discuss. Everything going okay? Everything going okay? Okay, yeah, your assignments look good. Your numbering method looks good. Everything going okay? Perfect. Everything going okay? Yep. May I check your numbering one more time? Oh, since the iso prefix is counted, is the iso prefix counted in alphabetical? Yes, it is. So the iso, if you count this way, you give the iso, which is I, a 4, and you want to give the thing that's first alphabetically the lowest number. Because if you count from right to left, you have a substituent of 4. The cycle will still get 5. But the isopropyl getting 4 compared to the methyl getting 4 is more beneficial. Okay. Yep. Does that make sense? It does. Perfect. How's everything going? Yep. Looks good. Yes, exactly. Yep. Looks good so far. Your counting method is correct. So, okay. Yes. We pick the one that's lowest alphabet. First, yeah. So, for example, isopropyl alkyne. Yep. So let's talk about this one. This may look innocuous, but this is actually designed to help me check to see if everyone understands the idea when there's a tie. So let's write our 2 potential carbon numbering methods. And you may say, well, which one is right? That requires a little more analysis in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, before I move any bit further, is there any difference in our numbering using both of these numbering methods? No. So there's no clear winner on that respect. So now we have to check the names. So for example, this 1 carbon substituent is a methyl group. What do we call this 5 carbon cyclic substituent? Yep, cyclopentyl. Okay, what do we call this 3 carbon substituent that's attached, where the main chain is attached at carbon 2? Isopropyl. Now my question to all of you is the iso prefix included when you're considering alphabetical order? Yes. So then, I comes before M. So what numbering method will we use? What numbering method places the smallest number on the substituent that's first in alphabetical order? Red. Yep, exactly right. So then we'd write this as 4. Wait. We're using the numbering method in red. But what goes first alphabetically? What's cyclopentyl? Yes. So then, what number do we assign to our cyclopentyl? 5. So we have 5 cyclopentyl. Then what's the next in alphabetical order? Isopropyl. And what number does it have using the red numbering convention? 4. So 5 cyclopentyl 4 isopropyl. And then finally, what's our carbon number for the methyl? 6. So 6 methyl. And then what do we call a 9 carbon chain? Nonane. There we go. Does that make sense? Okay, perfect. As you can see, we're slowly starting to name really complicated structures using these rules. So hopefully the buildup was relatively gradual. Let's now continue on. And let's just remember when naming compounds that the prefixes cyclo, iso, and neo are part of alphabetical order. Every other prefix you ignore. So I'd like you now to name the following 2 compounds. And I know it seems like we're just doing example after example, but that is the only way to learn nomenclature effectively. Just practice makes perfect. Everything going okay? Everything going okay? Yep, that's good. So this one, is there a more branch chain you can generate? Via counting method? What if you count it from the top? Oh no, no, the top chain is shorter. So yeah, you're right. You're right. Yep, that's fine. Everything going okay? Okay. Everything going okay? Perfect. Everything going okay? Yeah, that's fine so far. Yes. Yep. Yes. And so you only care about alphabetical order if there's a tie. Smallest number wins out first. Exactly right. Yes. Let's see. Yes. Everything going? Is it purple or apple? Purple. And then just remove other. It's fine. Yes. Yep. What goes first up? Oh, ISO is included alphabetically E before I. Yeah. Perfect. Everything going okay? Everything going okay? All right. 2, 3 dimethyl. Otherwise, it's perfect. Dimethyl. Oh,
Okay, I think I have some, but I'm not sure.
let's see. 2, 2, 4. Oh, the 2 wins out of the 3. Alphabetical order is only if it's a tie.
So otherwise you go left to right?
So if you count from left to right, you end up with a 2.
Oh, I see.
The counting method, they give you the smallest first number with a
Oh, yes.
Yes. No, so the ordering of the name is alphabetical, but the numbering method you choose gives is basically the smallest set of numbers. Does that make sense? Perfect. Everything going okay? So the dimethyl isn't counted. Otherwise, everything going okay? Oh, yeah. Okay. And have you tried the second? So to help everyone out, let's now come together and let's discuss the first one. Just the first one. I saw people are still working on the second. Really, the point of these problems is to give everyone enough practice. So there's no point unless you spend some time really working through it. That's how you memorize all of these different side chain names. So I'm going to count in two ways. 1, 2, 3, 4, 5, 6, 7. And I'm going to count in the opposite direction. 1, 2, 3, 4, 5, 6, 7. So which counting method gives me the smallest set of numbers? Just period. The smallest first number. Yep, exactly. So we're going to use that counting method. You only care about alphabetical order when there is a tie. So then, what substituent is at carbon 2? What do we call the substituent at carbon 2? Methyl. Okay, so we have a 2-methyl. What's the substituent at carbon 3? Methyl. So this is 3-methyl. What do we call the substituent at carbon 5? 2 carbons. What do we call that? Ethyl. Okay, so this is 5-ethyl. Okay, perfect. So what goes first? E or M? What's first alphabetically? E. So we'd call this 5-ethyl. And instead of, since we have 2 methyl groups, what do we call it? 2,3-dimethyl. Exactly. And then, now this is really important. The numbering method rules are different than the ordering in the name. The ordering in the name is alphabetical. The numbering rules for your structure are based on getting the smallest numbers. Does that make sense? So then, we have a 7-carbon chain. So what do we call it? Heptane. Okay, perfect, perfect. Now let's have you continue to work on the second structure. This one's quite interesting, so take a few more minutes to work through that. I'll be walking around to answer any questions. Yes. So there's 2 methods? Oh, so you write it down. Everything's going okay? Okay, I see a lot of reasonable answers. So let's now come together and discuss. Now, I'm going to try to find the longest carbon chain. So I'm going to count from the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's try to count in a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so which numbering method gives me the smallest first number? Yep. So then, and yes, you're correct, the longest carbon chain possible is 10. So then, looking at carbon 3, we have what substituents? Methyl. So I write this as 3-methyl, just for my note taking, 3-methyl. You need to include the locant for each substituent. Okay? Now, what do we call, attached to carbon 6, we have this chain here. It makes sort of a Y shape, and our main chain is attached to the quote-unquote primary carbon, making it a secondary carbon. Neopentyl would be 5. This is isobutyl. The key giveaway is the butyl chain has 4, and this is a 4-carbon chain. And what position is this isobutyl chain at? 6. Okay, finally, what else do we have at the 6th position? Ethyl. Now, in terms of alphabetical order, is the iso prefix counted in alphabetical order? Yes. Okay, so what goes first alphabetically? E, I, or M? E. Okay, so we name this as 6-ethyl. What's next? I or M? I. 6-isobutyl. Okay, then what? We have 2 methyls, so we name it as 3,3-dimethyl. Yep. Okay, and since we have a 10-carbon chain, what do we call it? Decane. Exactly. Does that make sense? Does that make sense to everyone? Okay, now we're going to shift gears and we're going to talk a lot. This next topic, if I had to pick, is one of the more important topics that we'll use again and again in multiple chapters. It's the idea of looking at the energy of a molecule based on how the atoms are arranged. So this is one topic where if you have your model kit, I would want you to follow along with your model kit. Basically take these notes home and try to retrace using the model kit the steps that we're going to do on the projector today, okay? This is one that it's a lot easier to see some of these effects when you have a model kit right in front of you. And we'll be definitely having some model kit pictures shown in this presentation. So, let's talk a little bit about molecular shape. How do we visualize molecular shape and the arrangement of atoms in our molecule? So, stereochemistry concerns the 3D arrangement of atoms in a molecule. So, carbon-carbon single bonds and other single bonds are rotatable. So, as a result, you can think of a carbon chain as a very floppy molecule. It's constantly rotating about its bonds, and it's constantly interconverting between different 3D arrangements of its atoms. Okay? So, conformation. So, a conformation is the 3D arrangement of atoms for a given molecule as the result of bond rotation. So, for example, we have our first conformation with a given 3D arrangement of atoms on the left, right? Now, if we rotate clockwise our carbon-carbon bond, if we rotate our carbon-carbon bond clockwise or counterclockwise, we end up with the following new conformation. Do you notice immediately how our hydrogens are in different arrangements of space, are in different regions of space? In the first example, our 2 hydrogens are opposite, right? This is known as an anti-configuration. In the second configuration, they are directly both up. And this is known as an eclipsed conformation. Different 3D arrangement of atoms.
Fine-tuning, right, because you're talking about.
The-
that
the-
on that
oh, the-
molecule and this on the other.
Yeah, looking at the two sets of white spheres, you notice how this hydrogen, let's put a circle around it. These two are on opposite sides, one's up, one's down. In the second conformation, both of our hydrogens are pointing up. Does that make sense? Perfect. Now, the most common way of visualizing the arrangement of atoms across a carbon-carbon bond is known as a Newman projection. It's a 3D drawing looking at the arrangement of atoms relative to a carbon-carbon bond. Okay, so starting off, let's pretend we have a carbon-carbon bond and we're looking at that carbon-carbon bond, right? So the black is our carbon and the red and green are our hydrogens. So in a sawhorse representation, which is a common way of drawing out substituents around a carbon-carbon bond, what we're doing quite simply is we are looking with our eyes from a side-on perspective. We're looking from a side-on perspective, sort of like if you walk next to a car, you're looking at the car from the side instead of from the front. And we're looking to see how are hydrogens arranged in 3D space. So, as we notice, we draw the relative 3D arrangement of our hydrogens out, and we draw out our carbon-carbon bond, so we're clearly able to see our carbon-carbon bond from this side-on perspective. I like to think of the sawhorse as like a side-on perspective. That's one way of drawing out substituents. The far more useful method is our Newman projection. And in our Newman projection, which I'm going to draw using a different color, the key feature of the Newman projection, which is our eye in purple, is we're looking at the substituents by looking directly down our carbon-carbon bond. Directly down our carbon-carbon bond. So we're walking around to the front of our car and we're looking at how are things arranged in 3D space. Does that make sense to everyone? Okay. So in a Newman projection, we are looking straight down our carbon-carbon bond. So our carbon-carbon bond in 3D space, the second carbon is behind the first. Is that clear? Now what we're going to do, the second carbon is not visible. So we're not going to explicitly draw it. We're going to draw out the arrangement of atoms first in our front plane. So all of the atoms in green are in the front. Okay, so we draw out the 3D arrangement of all the atoms in our front, right? So what's this first hydrogen? Is it up or down? Up. This one, is it on the left or right? Right, okay. So we go through that process, and then we look at all the carbon, we look at all the substituents, be them hydrogen, carbons, whatever, in the back. And then we indicate the 3D orientation of all of our carbons in the back. The key feature is the front carbon is visible, the back carbon is not. Does that make sense to everyone? Yes.
So in this case, the back carbon is represented by the ring.
It's behind the ring.
Okay, so what does the ring represent?
So the ring is just showing that the fact that the carbon-carbon bond can be rotated.
Okay.
And it's essentially showcasing the fact, the ring is partially showing the front carbon, saying the front carbon is blocking our view, the carbon-carbon bond is rotatable, and these hydrogens which are behind this circle are the hydrogens in the back. Does that make sense? Perfect. So now a key feature of many straight chain alkanes and many organic molecules is that at room temperature, there's enough energy for these molecules to constantly flop about and change their conformation. So molecules will constantly convert between different conformations, and different conformations have different energies. Okay, so that's really critical. Not all conformations are created equal. And what we're going to do in this chapter is we're going to be able to go from the 3D picture do a sawhorse, do a Newman projection, and then finally we'll be able to assess the energy of each of these conformations. That's our goal, okay? So to help you visualize Newman projections, I actually have a step-by-step guide. So pretend you're given the following alkyl chain. So this is a picture of what it would look like if you're playing with a model kit, okay? I always like to look at my carbon-carbon bond first from the side-on approach. What do we call the side-on view? Sawhorse, yep. So we look at it from the sawhorse view, and you make sure you draw all of your bonds, including CH bonds, because we care about our hydrogens in our Newman projection. Next, you're going to prepare a model of your structure. This is where the model kit comes in. And the reason why I have pictures is it's really hard if I'm standing up in the front just to mess around with a model kit that's like about this big. But we'll be passing some out, and we're more than welcome to do some additional practice problems with models next session. Okay. Now what you're going to do is you're going to take your Lewis structure. You're going to take your Lewis structure and you're going to rotate your Lewis structure 90 degrees. It can be to the right or to the left. I don't care. It doesn't actually matter. So if we take our model and we rotate it about 90 degrees to the right, we have a true sawhorse view, which is the key distinction for the sawhorse view is you're viewing it where the carbons are separated by a 45-degree angle. This is the other potential sawhorse view, which is a side-on view. So in this case, we're looking at it from this perspective. We're able to see all of our substituents, and can we see both of our carbons? Yeah. Do you see how the model reflects that sawhorse view? I can see both my carbons. I can see the arrangement of hydrogens relative to each other. Perfect. Everyone following so far? It's really hard to do these kinds of 3D manipulations in your head. This is why I like the model pictures. They keep things tangible. You know. Okay, so what's our next step? So what we're going to do next is we're going to take our model kit and we're going to look directly down one of our carbon atoms. So notice how I've turned my model kit, so I'm now staring directly down at one of my carbon atoms, okay? It doesn't matter which one you choose. You're going to draw all of the hydrogens in front of the circle, right? So we have these 3 hydrogens in front. Where's the first hydrogen? Is it pointing up or down? Up. So that's, oh, I drew the opposite Newman projection for this one. So we'll draw all of the substituents in front of our circle. These are the ones in red. All the substituents in back are behind the circle in blue. Does that make sense? So to showcase how we draw this specific Newman projection, let's do this one together. So I'm going to draw out my circle. So for my substituents in front, I'm going to do them in red. My first hydrogen is up. My second hydrogen is to the right, and my third hydrogen is to the left. Then, what about my back substituents? Is one of my hydrogens down? Yeah, so I'm going to draw that out. What about my other hydrogen? To the right, and the last one is to the left. The hydrogens in blue are behind the circle, so they're behind the first carbon. Does that make sense? Mm-hmm. Okay. Any other questions on this? Yes.
So the photo on the left is showing not rotated?
So this photo on the left and this Newman projection we just drew are identical.
So the one on the left
is the rotated form. Yeah. Okay, let's now try and practice. Let's take the following molecule and let's try to draw the Newman projection for this molecule. So we're going to do this example together just to make sure we're all on the same page. So first things first, let's draw out all of our hydrogens. Okay? Everyone okay so far? Now what I'm going to do is I'm going to rotate this entire molecule 90 degrees. 90 degrees. So that in turn gives me the following arrangement of atoms. So if I rotate it 90, this is carbon 1 and this is carbon 2. If I rotate it 90 degrees, what atom is going to be on front? Carbon 1. So then, what is attached to carbon 1? Bromine, right? So we'll draw out the bromine. What else is attached to carbon 1? Carbon. Yep, a methyl group that we'll write this as CH3. Yes.
Where do we put the two other carbons that stick out in the end?
The two other carbons that stick out for the end? Oh, they're attached to carbon 1 and attached to carbon 2. That's where the CH3 comes in.
Okay.
Does that make sense?
So how do we generally know where to assign, like, say, carbon 1 and 2?
So when drawing a Newman projection, so in this case, you'd be explicitly asked to look across a given bond. If it's not inherently indicated, you look across the most substituted set of carbons. So in this case, we're drawing the Newman projection across the bond between what we labeled as carbon 1 and carbon 2. But you can look across any set of atoms, any set of 2 carbon atoms you want. But often the analysis is centered on the more substituted atoms, as that provides, it's a much more information rich in terms of steric and other torsional interactions. Does that make sense? Perfect. So we have our front substituents. What are our 3 back substituents? What 3 substituents are attached to carbon 2, besides carbon 1, of course? Another bromine, yes, exactly right. What else? A methyl. And what else? Hydrogen, exactly right. Perfect. So now we have our sawhorse-like arrangement. Now in order to draw a Newman projection, what are we going to do? Where are we going to look? We're going to look directly down what? Our carbon, yep. So I'm going to look directly down carbon 1. Okay, so I'm going to draw carbon 1 in front. It actually doesn't matter which one you draw in front. Yes. So it's like drawing an eye. Yeah, it's just saying like I'm looking down that region. Yeah. So now if we're looking down carbon 1 is going to be in front. So let's draw out all of our substituents that are in front. Let's draw out all of our substituents that are in front. So what substituents are in front? What are attached to carbon 1? Yep, a methyl group. What else? Bromine, yep. And a hydrogen. Then I'm going to draw a circle. And then behind that circle, I'm going to draw all of my substituents that are attached to carbon 2. So let's do just that. So what 3 things are attached to carbon number 2? Yep, a hydrogen, a methyl, and a bromine. So these 2 portrayals of your molecule are exactly identical. They're referring to the same molecule. The beauty of the Newman projection is it provides us another lens for looking at a molecule and assessing its energy and any potential high energy interactions between substituents. Yes. Okay. So as it's 9 o'clock and the exam would have taken roughly 2 hours, and since I want us to be playing with model kits for this next part, I'm going to plan, if everyone's okay with it, that we'll stop here for today. But I want to make sure by Wednesday you bring your model kit to class, or you send me a message if you can't, so I can bring some model kits for us to play with. Is that okay? I would highly advise. It was the best $15 I spent on Amazon when I was a student, and it pays off. You'll need it for all your classes, and it really helps you go from this arrangement of lines to 3D reasoning. So we'll stop here, and I appreciate that everyone was so attentive today.